For a long time, individuals have imagined what life may be like in other universes. Because of the James Webb Space Telescope, the most astonishing telescope in existence, that question may finally be fit to be dissected. While noting the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have seen a few unequivocal peculiarities from one of the planets in the system, Proxima B. These irregularities, called artificial lights, have dazzled the mind in normal science. Yet what are they? Do these lights propose the presence of intelligent life on the world? Join us as we investigate the James Webb Space Telescope's disturbing discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of development, people have questioned whether there is life elsewhere in the universe. To conduct such an interstellar inquiry, American space specialists Jill Tarter and Thomas Pearson launched the search for extraterrestrial intelligence, or the SETI project, in 1984. The Foundation's goal is to gather spaceborne radio transmissions. Radio waves can travel farther and are thus more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the California Sierra Nevada mountains. Anyway, as of late, no definitive extraterrestrial signal has been found. Following that, the James Webb Space Telescope's successful launch supported the mission to examine a range of exoplanets circling distant stars. As the largest telescope on Earth, floating around 1 million miles from Earth and furnished with extraordinarily delicate markers, it has the potential to uncover momentous discoveries. A while back, there were no known planets outside our planetary system. Anyway, since then, more than 4,000 exoplanets have been found circling various stars. As indicated by NASA, the universe may contain millions of exoplanets. Early signs of something happening beyond our planetary system may be found in extraterrestrial vegetation. The Galileo spacecraft, on its course to Jupiter, turned its instruments back toward Earth and perceived an obvious indication of vegetation by seeing the vegetation red edge, a biosignature that consists of a blend of red and infrared light reflected by plants. For example, a planet like Earth covered in a jungle should have a strong and easily recognizable red edge signal. The James Webb Space Telescope, JWST, will measure the red edge of distant Earth-like planets in the habitable zone around stars, which could provide critical insights into what's happening underneath the surface of an exoplanet's atmosphere. When daylight crosses a planet's star, the JWST could potentially detect it as it enters the planet's atmosphere. The missing frequencies would then be seen through spectroscopy as particles and molecules in the atmosphere absorb specific frequency ranges, creating a unique fingerprint that the JWST can recognize. This technique may be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, made of a mix of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't commonly present, we might be able to detect intelligent life. For instance, chlorofluorocarbons, CFCs, compounds made for use in refrigeration and cleaning products, would almost certainly be detectable by extraterrestrials observing Earth's atmosphere from a distance. If the JWST detects CFCs in planetary atmospheres, it would be a decisive indication of mechanical progress. However, life on exoplanets may not look like life on Earth at all. Sometimes even ordinary living creatures like extremophiles, species that can survive in conditions where other living things would die, could seem extraterrestrial. These living beings, mostly microorganisms, can endure extreme conditions such as temperatures up to 250 degrees Fahrenheit or strong acids with pH levels under 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it may be wise to focus first on those ideal candidates. These planets could have temperatures that allow liquid water to exist on their surfaces as well as orbit a stable star. Our Sun is classified as a yellow G-type star. These stars are more limited and generally have shorter life expectancies. However, in our universe, the probability of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. This longer timescale allows for the development of life and the evolution of complex animals. Around 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a calm red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, could have liquid water on their surfaces. Notwithstanding its smaller size and cooler mass compared to our Sun, the TRAPPIST-1 star emits light similar to that of Earth's Sunday. Due to the close orbit of its planets, the most promising chance to detect city lights outside our solar system may be Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is much dimmer than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life due to the presence of liquid water. In August 2016, astronomers found a planet with 1.3 Earth masses in the habitable zone, a Goldilocks zone where the light intensity is ideal for liquid water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, inert planet. Considering that it orbits its red dwarf star at a distance of just 4.6 million miles, this close orbit exposes it to intense solar winds that could strip away its atmosphere. Nevertheless, Proxima B gets enough sunlight for temperatures and liquid water to exist, similar to Earth. Due to its proximity to its star, Proxima B is believed to be tidally locked, always showing the same side to the star, much like the Moon does with Earth. Proxima Centauri is around 18% the mass of the Sun and emits substantially less light, only 5% of the Sun's brightness. Could appear to be a barren, burned planet. However, liquid water could exist on Proxima B as long as the planet has an atmosphere to retain heat. Since the total energy reaching it from the Sun is only 65% of what Earth receives, the planet may not be especially hospitable to life. Still, it remains the best candidate due to its tidal locking, which means it always faces the same side toward the star, resulting in permanent light and night with extreme temperature variations. Proxima also receives almost 3 times the amount of high-energy radiation that Earth does, including X-rays and ultraviolet light. Due to its proximity to Proxima Centauri, Proxima B is constantly bombarded by high-energy particles during solar flares. Unless it has a protective magnetic field like Earth's, the conditions for life may not be ideal. Still, favorable conditions could potentially make Proxima B a more inviting world. Unfortunately, models suggest that the atmospheres of tidally locked planets may be prone to rapid breakdown due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we don't have substantial information on Proxima B's volcanic activity or magnetic field strength, we can't definitively measure whether the planet has an atmosphere. However, since an atmosphere suggests the presence of seas, and both together suggest the potential for life, there is great hope to determine whether Proxima B has a complex biosphere. It might have solar-powered charging stations covering the day side to generate energy, lighting, and warming the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has sparked a rush to determine if it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, enabling them to assess its density and confirm its rocky composition, offering clues about the materials that make up its surface. During a transit, starlight could pass through the planet's atmosphere. However, the likelihood that the orbit will be in the right alignment for scientists to observe a transit is only 1.5%. The star's tendency to erupt further complicates matters. Astronomer David Kipping of Columbia University states that the star is unstable, as solar flares cause a rocky planet to absorb sunlight and remit it as infrared light. Nevertheless, rocky planets produce a particular type of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was specifically designed to detect infrared light. Proxima B's infrared signature is critical to identifying the planet's atmosphere. Also, the JWST's infrared capabilities are infinitely better than Hubble's, which could allow it to detect city lights on Proxima B's night side, even if they are as weak as those on Earth. The JWST could identify artificial lighting if it is restricted to a frequency band much smaller than the star's light. Proxima B's dayside may be heavily covered with solar panels reflecting sunlight. As Proxima B orbits its star, it faces a consistent pattern of day and night with extreme temperature variations. The temperature contrast between day and night will depend on whether the planet is entirely made of exposed rock or if it lacks an atmosphere. Proxima B's temperatures will change dramatically, as the day side will radiate all the energy it receives from Proxima Centauri as blackbody radiation. The night side, on the other hand, would resemble a frozen wasteland. If the temperature contrast between day and night is less pronounced, we can deduce the presence of an atmosphere. It will take the JWST just 11.2 Earth days to gather enough data to detect the first artificial city lights on Proxima B's night side, lights that could prove intelligent life exists beyond our solar system. Given the study's conclusions, Proxima B may harbor hidden secrets. Perhaps the daytime of Proxima B generates abundant solar energy, and the lights could offer evidence of a vibrant and technologically advanced society. While the presence of artificial lighting on Proxima B would be a groundbreaking discovery, scientists are proceeding cautiously. The detection of such lights could suggest an advanced civilization, but there are numerous other potential explanations for these signals. The technology that the James Webb Space Telescope uses to examine distant worlds is still in its infancy, and astronomers are just beginning to refine their methods. The lights detected could be natural phenomena, reflections from surface features like volcanic eruptions, lightning storms, or even unusual atmospheric phenomena that might mimic artificial lighting. It's essential for scientists to continue their research and cross-check their findings. In fact, the James Webb Space Telescope will continue observing Proxima B, as well as other potentially habitable exoplanets, to build a broader understanding of their atmospheres and surface conditions. The detection of artificial lights would also be followed by years of further exploration to confirm their origins. If the signals do indeed originate from intelligent life, it would represent one of the most profound scientific discoveries in human history. The excitement surrounding Proxima B and other exoplanets doesn't just stem from the hope of finding life. It also raises broader philosophical questions about humanity's place in the cosmos. The discovery of alien civilizations would force us to rethink the uniqueness of life on Earth. It could lead to an era of unprecedented collaboration between nations, as the discovery of extraterrestrial life would unite humanity with a shared sense of curiosity and awe. It would also underscore the importance of space exploration, pushing us to invest in new technologies that will allow us to continue searching for answers in the distant reaches of the universe. For now, the search for city lights on Proxima B serves as a tantalizing possibility, one that may soon reveal whether we are truly alone in the universe. As the James Webb Space Telescope sends back more data, the dream of finding signs of intelligent life beyond Earth becomes more real, drawing us ever closer to answering one of the greatest questions in science. Whether or not Proxima B harbors an advanced civilization, this discovery could be the key to unlocking the future of space exploration and interstellar communication. As we continue to push the boundaries of what's possible, the next generation of astronomers, scientists, and explorers may well be the ones to confirm what was once thought impossible: that life, in all its forms, is more common than we ever imagined.